This is a quick video on Jensen's inequality. So this is the equality that we're trying to prove here at the top. Now, why you might want to use this inequality, why this is helpful? Well, if we had a random variable x, then we can tell whether or not a function of that random variable is going to be greater or larger than x if that is a linear function. And we can determine that pretty quickly. But if we have some other function g of x, which is not linear, figuring out what the relationship is between x and that function might be more difficult. So Jensen's inequality gives us a clue as for convex functions instead of linear functions. Now, to prove this, we're going to remember, or we're going to have to review Taylor's series expansion. So remember, with the Taylor series, we can approximate a function f of x around the neighborhood of a. So there'll be a function, and then we'll have some point a, which is in the support or the domain of the function, and we'll be able to approximate the function f of x around that neighborhood a. We can do this with the function f of a, x minus a, 0, 0 factorial, plus f of a, first derivative, x minus a to the power of 1 over 1 factorial, and we continue this pattern. So this Taylor series approximation is the same thing as saying the sum from I equals 0 to infinity, f to the ith derivative evaluated at a, x minus a to the power of I over I factorial. And we can approximate the function to a certain degree. We don't have to go all the way infinity points. We can just stop at 1 or 2 or so on. So the other thing that we need to remember is about convex functions in general. Now, for this Jensen's inequality, we're specifically talking about g of x, where g of x is a convex function. For a convex function, if we were to draw the function, draw a convex function, a property of convex functions is that a tangent line at any particular point is always going to be less than the function. This is because a convex function has that the slope is always increasing. Now we can approximate a function g of x to the second degree around point A using this line here, which is the same line as our tangent line, which gives us a tangent line of g of x at A. Now for convex functions in particular, the convex function is always larger than the tangent line. So we have, if g of x is convex, this means that g of x is greater than or equal to g of a plus the derivative of g evaluated at a times x minus a. Now, if we let a be x of a, or the expected value of x, which is just a constant, that's just a number, so that's fine, and this is x-axis here, so expected value of x should be in our support of x. Then this function above becomes g of x less than or equal to expected value of x, g evaluated at the expected value of x, plus the derivative of g evaluated at the expected value of x times x minus the expected value of x. Then we take the expected value of both sides, expected value of g of x is greater than or equal. Now, by properties of expected value, even if we had some sort of dependent relationship, we can break up the expected value by summation and minus signs, so linear functions can be broken up. So this becomes the expected value of g evaluated at e of x. This becomes, so g, the derivative of g evaluated at e of x is just a constant. And then over here, we would have the expected value of x minus the expected value of x, because the expected value of the expected value of x is just the expected value of x. So this whole term becomes 0. Now the expected value of g evaluated at e of x, this is also just a constant. So this becomes e to the expected value of g of x greater than or equal to g evaluated at the expected value of x. And that's it. That proves our result.